Resonance circuit and electrical resonance. That is what we are going to discuss. A combination of inductance coil, capacitor and resistance is called a resonance circuit. We have seen the analysis of the circuit in an earlier posting, and where we have seen that impedance of the LCR circuit is Z equals square root of R square plus omega L minus 1 by omega C the whole square. Suppose omega L equals 1 by omega C. Then what is Z? Then Z becomes, this term reduces to 0. Then Z equals square root of R square, or Z equals R. That is, Z is a minimum because its factor is 0. And the minimum value of impedance is equal to resistance in the circuit. Reactances of these two elements cancel each other, and total impedance of the circuit reduces to R. So now the current in the circuit, these all are all RMS values. So current in the circuit I equals V by Z. Now at resonance Z equals R. So IR equals V by R. This is the maximum current in the circuit. Now this phenomenon is referred to as resonance. Resonance of in electricity, or resonance in alternating current circuits, is the attainment of maximum current in an LCR circuit at a particular frequency of the AC. The condition for resonance is capacitor reactance must be omega L must be equal to, capacitive reactance 1 by omega C must be equal to inductive reactance omega L. Under this condition, current in the circuit becomes maximum. This phenomenon is referred to as resonance in AC circuits. Now from this expression, we can solve omega L equals 1 by omega C. Just you cross multiply this, you get omega square LC equals 1, from which omega equals 1 by square root of LC. So frequency F equals omega by 2 pi. We denote it as by letter FR, called resonant frequency, equals omega by 2 pi, that is 1 by 2 pi root of LC. That means an AC of this frequency produces maximum current in this circuit. When a group of frequencies, if the source supplies AC at different frequencies to the circuit, and if that group of frequencies contains this particular frequency 1 by 2 pi root of LC, the circuit will conduct this particular frequency AC with maximum current. That is, this circuit selects a particular frequency AC from a group. Hence, this circuit is also known as selective circuit. It can absorb or conduct or pass a particular frequency AC at its maximum or with maximum current, omitting all other frequencies, because this circuit will offer more resistance to other frequencies except this frequency 1 by 2 pi root of LC. This is the speciality of resonant circuit. It can select a particular frequency from a group of frequencies. This is very important in communication systems. We will discuss it uh, when we discuss communication systems. Now, if you draw a graph between frequency on the horizontal axis and current along the vertical axis, you get a graph of this shape. Now see, impedance of the circuit is Z equals square root of R square plus omega L minus 1 by omega C the whole square. Now at lower frequencies, for low frequency ACs, omega is small. That means this factor is small, but 1 by omega C becomes large because omega is small. So this quantity at lower frequency, the terms within the brackets becomes large. So Z is also large. That means current will be less. So at low frequencies, current is small. Current conducted by the circuit is small. When the frequency is very high, this term becomes predominant. Omega L becomes large. This becomes small. So on the total, this term in the bracket is high now also. So that Z is also high. That means current is small. So at small frequencies and higher frequencies, Z is high and current conducted by the circuit is small. That is why the graph falls off at low frequency side and high frequency side. But for at the particular frequency FR, current is maximum. That is at resonance. So this is reason why the graph takes this shape. Now at resonance, I equals IR equals V by R. So maximum current at resonance depends on resistance in the circuit. If R is small, IR is large. If R is large, IR is small. That is why, say, for three different resistance values, here the graphs are shown. This graph represents smaller value of R. This is for high value of R. So the graph, height of the graph depends on resistance in the circuit. Now another property of this resonant circuit, VR, VL, VC. Then the total applied voltage V. We have seen these things in an earlier posting. V square equals VR square plus VL minus VC the whole square. That was the voltage equation. So for V equals square root of VR square plus VL minus VC the whole square. Now at resonance, VL is equal to VC because omega L equals 1 by omega C. So I into omega L, that is VL, equals I into 1 by omega C, that is VC. So at resonance, the VL equals VC, so that V equals the square root of VR square or V equals VR. That is the applied voltage is equal to voltage across the resistance. VR is I into R. Now, at the same time, the voltage appears across L and C. They cancel each other, that's all, when they combine. But individually, there is a particular voltage, definite voltage across inductance coil or capacitor. Now, voltage across inductance VL equals I into XL. I is maximum at resonance. This is the current at resonance. That is I into omega L. Similarly, Vc equals I into Xc equals I into 1 by omega C. Then you take the ratio of VL by applied voltage. That is I into omega L by V is now V equals VR at resonance. So VR is I into R. That means VL by V equals omega L by R. Now, V is the applied voltage. VL is the voltage developed across the inductance coil. Now, by making R very small, if R is very small compared to omega L, or omega L is much greater than R, VL will be greater than V. What does it mean? This voltage across the coil becomes very large when compared to the applied voltage at resonance. That is, voltage is magnified across the inductance coil. That is one special property of resonance circuit. You can tap higher voltage than the applied voltage when resonance occurs, or the circuit magnifies voltage. This is used in incandescent tube light in our home circuits. The tube lights require about more than 404 volt for its working, but we are getting only 230 to 40 volt from the line. So it must be magnified for the working of the incandescent tube, older type tubes. Now, so same thing happens across the capacitor also. So at resonance, voltage across inductance coil or voltage across the capacitance coil will be much greater than the applied voltage, provided R is very small. You keep the resistance value small in the circuit. Then at resonance, you can get higher voltage than applied from the inductance coil or capacitance. This is called voltage magnification. So voltage magnification is defined as the ratio of voltage across the inductance coil or capacitance to the applied voltage, or it is equal to the ratio of the inductive reactance to resistance or capacitive reactance to resistance. Omega L by R or 1 by omega C by R, that is 1 by omega C R. This is the voltage magnification associated with LCR circuits at resonance. Now we discuss about some more properties of resonance circuits. We know that at resonance, the circuit current is maximum and circuit impedance is equal to resistance in this circuit. So at resonance, the LCR circuit behaves purely as a resistive circuit, so that its power factor is 1. Because there is no phase difference between voltage and current. So phi is 0. So power factor is cos 0, 1. So it absorbs maximum power because it behaves like a resistive circuit and power factor is 1. Now power consumed at resonance, PR equals I square into R. In effect, the circuit behaves like a resistive circuit. So power consumed is mainly caused by the resistance in the circuit. That is IR square into current at resonance, IR square into R. Or it is V square by R. Suppose, so this is maximum. This is a maximum. So at resonance, the circuit consumes maximum power. Then suppose omega L minus 1 by omega C is equal to numerical value of the resistance in the circuit. When these two are equal, we get resonance. When this minus this is equal to R, then what is Z? Z is square root of R square plus this square. This is now R. So Z equals square root of R square plus R square. That is root 2 R. Now the current in the circuit is V by Z, that is V by root 2 R. V by R is IR. V by R is current at resonance IR. So this is now the current is I equals I by IR by root 2. So that power consumed under this condition P equals I square R. That is, I square is IR by root 2 square, or IR square R by 2. IR square R is PR, power at resonance. So P equals PR by 2. When this minus this is equal to R. That is a special case. Under this condition, power consumed is half of the power consumed at resonance. See this graph. This is the graph between power and frequency. Graph is has a shape similar to that of the current frequency graph. Now at resonance, power is maximum, and that is at resonant frequency FR 1 by 2 pi root of LC. Now this is PR by 2, half of this. Now if you draw a horizontal line like this, it will cut the graph at 2 points. One corresponds to a frequency F1 and the other corresponds to frequency F2. So these two frequencies, there are two frequencies which are responsible for the power consumed to be half of the maximum power at resonance. These are called F1 and F2 are called cutoff frequencies. At these frequencies, the circuit consumes half of the power consumed at resonance. And F1 is the smaller one. F1 is called the lower cutoff frequency, and F2 is called upper cutoff frequencies. The difference between these two frequencies, that is F2 minus F1, is called the bandwidth of the circuit. Bandwidth of the circuit. We will discuss the significance of these things when we discuss questions in QMaster. I will post it immediately. QMasters will come in series, as a serial. Okay, then there is yet another point. Now, in simple form, between F1 and F2, the curve is this. If the curve is somewhat flat, that means this circuit conducts AC of frequencies in between F1 and F2 almost equally. And the significance of that point we will discuss. It is very important in communication. Now, There is another quantity associated with the resonance circuit that is called the quality factor, Q. Q equals is defined as FR, resonant frequency by bandwidth, FR by F2 minus F1. It can be shown to be equal to omega L by R or 1 by omega C. This is nothing but magnification factor. So quality factor and magnification factor have the same formula. The rest of the AC circuits we will discuss in the form of question master, questions and answers, problems, etc. I will post it immediately. Thank you. So keep viewing my videos, subscribe the video and try to view earlier postings. Then only you will get the basics and understand the subject fully. Thank you.